So let's turn this into a mathematical puzzle. And actually, I think what we'll end up doing is sort of reverse engineering how this was actually designed. So let's go over the rules that we had for moves again. I have a fixed set of moves, so I can do any at any time. I can do nothing. In other words, just holding it, I can think like, I just did a move. I did some more. Look at that! Wow. A few more times practicing, then I'll be able to do as well as that kid did. And others, I can reverse any move, and the moves don't depend on the current state. So I'm just repeating what I said before, but I want to axiomatize this mathematically now and see that we can do the same sort of things in the mathematical object called a group. So the corresponding thing for we have a finite set of moves doable at any time is I have a set together with a multiplication. And I should think of the set as parameterizing the moves I can do, and the multiplication as parameterizing do this one, then do this one. So now my moves aren't just sort of the single turn this once, turn this once. It can be a sequence. Do this sequence of turns, but that's still a perfectly valid move. And I'm considering all of those. I have an identity element for my multiplication. So in other words, this is the same as my do nothing. So I have an element that if I do it after A or do it before A, that's the same as just doing A. And then all my moves are supposed to be reversible, so I'm supposed to have inverses. In other words, if A is fixed, I'm supposed to be able to find a B, so that if I do B and then I do A, it's the same as not doing anything. And if I do A and then do B, it's also the same as not doing anything. And then lastly, the one that's like moves don't depend on the current state, my multiplication is supposed to be associative. So in other words, I should think of this as saying do C and then do BA. Or I can do B and C first and then do A. And if you think conceptually, I'm not doing anything. Both of these signs are parameterizing do C, then do B, then do A. It's just how am I grouping them to name them. Okay, so groups are things that you've probably actually dealt with and you run into a lot of times. So first, the real numbers under addition to a group. Why is this? Well, I'm supposed to have a set, that's the real numbers, together with a multiplication. The multiplication I'm calling addition. And then I have these axioms to check. First of all, is there an identity? Zero. You know this is actually basic arithmetic. 0 is the additive identity. Are there inverses? Negative numbers. The negative of any numbers is additive inverse. And then, is it associative? Yes, we just all accept that addition is associative. So, there we go. Another one, real numbers under multiplication. This one's a slight lie, because of course, as I go down and check, I have a set. I have a multiplication, namely multiplication. Do I have an additive identity? A multiplicative identity. Yeah, 1, which is fine. Do I have inverses? Usually. Ooh, do I have inverses? Oh, where does inverses break down? 0. So I should say the non-zero real numbers with multiplication. If I throw out 0, I still have a set, I still have a multiplication, and I have inverses. So that works just as well. The integers under addition, that gives me another one, even easier than the real numbers. And then slightly more complicated ones, the integers modulo n. So I'll write this as z mod n, and I'll come back to it later. So this is just a set of numbers between 0 and n minus 1 inclusive. And you imagine putting these around a clock, and my clock is going to have, my day is going to have n hours in it. And you just tell time using an n-hour day. So I know how to add hours, you know, if it's before noon, or I guess I really should do maybe a 24-hour clock. If it's before midnight, then I just keep adding hours the way I would normally add them. But once I reach midnight, I go from 23 o'clock to 0 o'clock again. So same thing. I keep adding 1, and I start at 0, and I work my way up, and I add 1 until I get to n minus 1, but then I reach n minus 1. If I add 1 again, I go back to 0. And you can check that this gives you a group. 0 is the additive identity, and then every number has an inverse. And the easiest one to check is, what's the inverse of 1? Well, what is the inverse of 1? N minus 1. time version of my day, then 1 hour added to 23 o'clock gets me back to 0. So same sort of idea. Now one that's a little more complicated. If you give me a finite set x, I can look at those functions that are one-to-one and onto on x. So what's onto mean? It means that if you give me any element of my set, let's call it y, I can find some x in my set such that f of x is y. Another way to say it, function surjective. Every element in x is the image of something in x under my function. One-to-one means if I have two things that map to the same element, then they were actually the same element. So these two conditions, if you think back to calculus, one-to-one meant my function satisfies what's often called the horizontal line test. So if I drew a horizontal line, if I drew the graph of my function and then a horizontal line, it's going to hit at exactly 1 point. If you think just in, when you're normally looking at, say, one variable calculus, we say it hits in at most 1 point, and then it's one-to-one. So one-to-one says it hits in at most 1 point, onto says it hits in at least 1 point. And so together, I get that it hits in exactly 1 point. So these functions form a group under composition. If I do one function and then another, I'm still taking a function from x to itself. And the one-to-one and onto means they're all invertible functions. So it's worthwhile to sort of play around with some of these and write out some examples if your set has, say, 3 elements. If your set has 2 elements, I can actually use my hands to describe both of them. 3 elements is going to be tougher. So I can ask, where does this finger go? And where does this finger go? And then I'll describe where they go in terms of the positions, because it's also pretty easy. So what's a function that takes these 2 positions to these 2 positions? Okay. The identity. It's the same one that we've dealt with before. It's the one that's, in this case, don't move my hands at all. This one goes to where it is. This one goes to where it is. That's a perfectly good function. What's another one? My right hand is now in the left hand position, and my left hand is in the right hand position. And you have to imagine that I didn't have arms, that in fact it was only the movement of my fingertips that mattered. So if I did this, and then I did it again, well, now I run into the fact that I do have arms. But I'm back where I started from. I only care about where my fingertips go, and the right hand ended up in the right spot, and the left hand ended up in the left spot. So that's the same as the identity. If I had 3 elements, you can check that there are 6 different functions, if I have 3, that satisfy these conditions. So this gives me a group, and I'll name this group, I'll call this the symmetric group on X. So I'll probably call it that again later. So one of the ways that it's easiest to describe a multiplication on a group is actually to write out a so-called Cayley table, where I see the elements in my group. In this case, I'm looking at Z mod 3. So I've listed the elements of the group at the top, and I've listed them along the left. And then what goes in the middle is just a table recording the addition. So 0 and 0 is 0, 0 and 1 is 1, 0 and 2 is 2, 1 and 1 is 2, 2 and 2 is 1, and so on. So you can see this square table records all of the information about the multiplication of the group. We'll come back and see these Cayley tables again, actually, at the end, when we're talking about things that you see in stereo.